All right. Okay, so thank you, Fedor, for the nice introduction. And also thank you for inviting me to present our work here. So as you already told the others, I will talk about r2SCAN-3c STO, which is an efficient, robust, and reliable composite DFT method in ADF. This is my overview for today. So first of all, I want to introduce you to the 3C family of methods. Then I will talk about r2SCAN-3c STO in general. I will show you some results, give you a conclusion, and in the end also give you a short demo or demonstrate you how to do a single point calculation with r2SCAN-3c. All right, so the first thing right now is the introduction to the 3C family. So in a working group, there were some several methods we developed with this 3C tag. And this 3C basically just stands for 3 corrections. And this table, I marked every correction in green here. So the first method that was developed is Hartree-Fock-3c, so HR3c. It applies, so it's basically a simple Hartree-Fock calculation, which applies minimal basis set, the D3 dispersion correction, a short range bond correction, as well as a basis set superposition error correction. In this case, it's the geometrical counterpoise correction, which is based on the Voigt-Bernardi counterpoise correction. Then the first composite DFT method was PBH3c, developed in our group. It's a hybrid based on PBE, and it has 42% Fock exchange. It applies a small basis set termed MSVP, where the M stands for modified, the D3 dispersion correction, as well as the GCP correction. Afterwards, then came B97-3c, which is a meta DGA, which applies a bigger basis set, so the MTZVP basis set, the D3 dispersion correction, as well as a short range bond correction. And then finally, r2SCAN-3c was developed, which applies an even bigger basis set termed MTZVPP, so it's doubly polarized. The density function itself is unaltered, and it applies the D4 dispersion correction now, which is the successor of D3, and also the GCP BSSE correction. Upon this point, every method has only been developed with Gaussian type orbitals, so with GTOs. So we thought, why not also test it with STOs, so theta type orbitals. That's why we then also choose the MTZ2P basis set, but I will talk about this right now. So now I will introduce you to r2SCAN-3c STO. It basically consists of these 4 pillars. So the density functional r2SCAN, the basis set MTZ2P, the dispersion correction, and the BSSE correction. And now I will go through every pillar and explain you a bit more about it. First of all, the density functional r2SCAN. It stems from the scan functional, which was proposed by Purdue et al. In 2015, and it stands for strongly constrained and appropriately normed density functional. I think it was quite popular back then, but it turns out that it's quite grid sensitive. So on the right side, I'm showing you the mean absolute deviation for the G3 energy benchmark set, and which is plotted relative to the relative grid point count. And here in gray, you can see the result with scan, and especially over here, you see that the errors become quite large, even though that shouldn't be the case. So there are, it's quite grid sensitive. Then in 2019, Bartok et al. Proposed the regularized strong scan functional, or short r-scan. For this, you can see the results over here. There's now no grid sensitivity anymore, but the accuracy went down quite dramatically, so it's actually not really usable. And then in 2020, Furness et al. Proposed the regularized restored scan functional, or short r2SCAN. And for this, you can see the results down here. There, the grid sensitivity is not so large anymore, and the accuracy is even better than with scan. So it's the perfect basis to do a DFT composite method such as r2SCAN-3c. However, we still observed some grid sensitivities when we tested it, so we also tested it in ADF. For this, I'm showing you this graph over here, plotting you the mean absolute deviation for these benchmark sets. And we tested different settings for the density fitting grid, so the ZLM fit, which range from basic to excellent on the x-axis. And in colors, we're showing different settings for the Becky integration grid. Now, if you look for the density fitting, there's actually almost no change at all if you go from left to right. But if you look at the colors, it's only converged if you take the yellow curve, so the good Becky grid. So in the end, we just settled with the good Becky grid as well as the good density fitting, just to be sure that everything works fine. And both of them are combined with the numerical quality, which is then set to good as default for r2SCAN-3c STO. Right, so then the next pillar is the basis set termed MTZ2P. It's basically just a combination of different basis sets that are already available in ADF. So for hydrogen and helium, the DZP basis set is used. For nitrogen, oxygen, and the other elements over here, the TZ2P basis set is used. And for the remaining elements, then the TZP basis set is used. As you can see, there are two asterisks over here for hydrogen, oxygen. There we changed the exponents of the polarization functions. For hydrogen, we changed it from 1.25 to 1.70, and for oxygen from 2 to 2.15, as we got better results with that. Then on the right side, I'm showing you the contraction schemes where I compare the original GTO method with the STO method. And you can see that for hydrogen, there's exactly the same contraction. For carbon, it's also exactly the same. But for oxygen, for example, there are two depolarization functions with the GTO, where there's one D and one F function for the STO. And we somehow try to replace the one F function with another D function just to resample the original basis set, but we weren't lucky, so in the end we just stayed. And now also for heavier elements, I wanted to show you the contraction scheme since there are a lot more basis functions available for STOs. The reason for that is now that we use an explicit relativistic treatment, so we need an all-electron basis set. Per default, we use scalar relativistic Zora with the STO approach, which is then used instead of the effective core potentials used in the GTO approach. Right, so now the third pillar is the dispersion correction. As I told you before, we use GRIMME'S for dispersion correction. It's an energy and gradient correction, which includes three body interactions with the Axel-Short-Teller-Mutoh term, or in short, ATM term. Also, charge information is considered and the geometry input is required to calculate it. Computation usually just takes a few seconds or is even faster than 1 second, so it's basically for free. On the right side, I'm showing you the parameters for it. It's just if you're familiar with D3 or D4, but it's not very important right now. I only want to show you that going from the GTOs to the STOs, we just changed one parameter, the S9, which scaled down from 2 to 1.53, and this just scales down the ATM terms or the three-body interactions. Now the last pillar is the BSSE correction. For this, we use the geometrical counterpoise correction. It accounts for the base set superposition error, but in the case of r2SCAN-3c, it also includes the basis set incompleteness error. So it's just fitted into the correction. It's also just an additive term, such as the D4 correction. It's an energy and gradient term, correction term, and depends on the basis set, and also requires the geometry. The computation is even faster than with D4, so it's also for free, you could say. We changed only the global scaling parameter sigma going from the GTOs to the STOs, and this parameter basically just scales the GCP contributions. So if it's set to 0, the GCP correction is turned off, and we scaled it down from 1 to 0.879. Now you might wonder how large is the influence of the GCP correction. So for this, I'm showing you here this WATER27 benchmark set. So I'm showing you the deviation for each system. And we changed the sigma value, which then scales the GCP correction. So if it's set to 0, which you can see in gray, GCP correction is turned off. And if it's set to 1, it's the default value. Now, if you look at this graph, you can see that especially in these systems, which are WATER20 clusters, the errors have an amount of 30 kcal per mole, which is just unacceptable. And then when you turn on the GCP correction, the errors just go down until we reach the blue line over here, which we then took as default setting. All right, so now we have everything we need to calculate the energy with r2SCAN-3c. So I'm giving you the energy expression down here. It's the electronic energy calculated with r2SCAN in combination with the MTZ2P basis set. And on top of that, the D4 dispersion correction and the GCP correction are just added. Okay, so now we have everything, so I can show you the results calculated with r2SCAN-3c. First of all, I'm going to show you the geometries. So I have 4 geometry benchmark sets here for light main group bonds, for heavy main group bonds, for long bond lengths, and for transition metal catalysts, where we also look at the bond lengths. And we tested in blue r2SCAN-3c with STOs, in yellow with GTOs. And we also tested BP8064 with a TZP basis set in gray and M062X with a TZP basis set in green. Now, if we look at these graphs, we see that the mean deviation is almost the same between the STOs and GTOs, but the standard deviation is a bit larger, but I think that's not really a problem. So overall, the performance is more or less the same. And we also see that, for example, for light main group bonds, we see that the hybrid, meta hybrid M062X has even a larger standard deviation. So we're quite happy with the results. Okay, then we tested a lot of energy benchmark sets. First of all, general main group energies. For this, we usually evaluate the GMTKN55 benchmark set collection, which is just a benchmark set collection with 55 benchmark sets, which can be categorized into basic properties, reactions, barriers, inter and intramolecular non-covalent interactions, and just then in total. And since the interaction energies have a very large range, we just scale them in order to compare them. So we use the weighted MAD2, or in short, WTMAD2, to evaluate the benchmark collection. And here is the formula for this. So we weight each MAD for each benchmark set with this factor. And the 57.82 is just the mean absolute of every data point, so of every reference point, which is then divided by the mean absolute of each benchmark set. Okay, so now in blue, I'm showing you again the r2SCAN-3c with STOs results, in yellow with GTOs, in gray is now the meta GGA M06LD3 with a QZ basis set, and in green PBE0 with a QZ base set, so a hybrid. Now, if we compare for basic properties, the r2SCAN-3c STO with a hybrid PB0, we see that there's almost no difference at all. So that's really nice. For reactions, it's even a bit better, while another meta GGA such as M06L fails here. For barriers, it's the opposite, but here it's expected as hybrids just yield better results for barriers. Then for inter and intramolecular non-covalent interactions, it's also almost the same if you compare r2SCAN-3c with PB0, which is really nice. And also in total, the weighted MAD is only slightly worse than with PB0, so that's really impressive, I would say. Okay, since the GMTKN only covers general main group elements, it's also important to investigate other benchmark sets. So here I'm showing you the IMPI19. It's a benchmark set for IMPI interactions, and here I'm only showing you the deviations of each data point, and I'm comparing the original GTO approach with the STO approach. So GTO again in yellow, STO in blue. And as you can see, each data point is quite different if you compare them. So it's really important that if you use r2SCAN-3c with STOs, that you also put the STO in parentheses afterwards if you cite it, for example. Now looking at this plot, we see that especially in the systems over here, we get way better results with the STOs. This is also visible in the MAD. In general, we also saw in other benchmark sets that pi interactions are really well described with the STOs. So then the next topic are conformational energies. So in our working group, we usually work with conformal ensembles, which we generate with CREST and XCB. And afterwards, we optimize them and re-rank them with DFT. And for this, we usually use r2SCAN-3c as it yields very good results for conformational energies. So it was really important that we maintain this accuracy. So here I'm showing you the relative energies for the ACONF12 benchmark set, which is a benchmark set for conformation energies of long alkane chains. In gray is the reference, yellow is again GTO, blue is STO. And you can see that the Pearson correlation coefficient is even better with STOs, so that's really nice. In this case, it's even better if the shape of the graph is the same instead of the error. Of course, the errors are also important, but the shape is more important for conformational energies. All right. So now the last energy benchmark set is the MOR 41 I'm showing you today. Here we test on organometallic chemistry, and you can see here that the points are not so different as before. In most cases, they're more or less the same. We have some outliers, such as this one, for example, but we also have positive outliers like here in this area. And if you look at the molecule, we see here's a CP star ruthenium interaction. So it's again a pi interaction. And here the STOs, of course, shine. All right, so now I also want to show you some computation times. For this, we just took A structures from these benchmark sets and calculated the MAD, and, which I show you in blue. And I'm also showing you wall time quotients in yellow, which are just the wall times divided by the wall time of r2SCAN-3c. And now if we look, for example, at the first 3 bars, you can compare r2SCAN-3c with r2SCAN-TZP and r2SCAN-TZ2p. And while the basis sets are increased, the MAD is also increased, and also the wall time quotient increases. So we are faster and also more accurate, also faster and more accurate than TPSS, for example. We could also compare r2SCAN-3c maybe with PB0QZ4p. Here the MAD is almost the same, while the computation time is 10 times slower. Or we could also compare it to the parent scan with the QZ4p basis set. Here the MAD is even a bit larger, and it's 16 times slower. So it's really impressive what we could achieve with r2SCAN-3c. Right, so that's basically it for the information part, I guess. So I'm giving you a conclusion. So in comparison to the original GTO approach, there's now modified MTZ2P basis sets, and the D4 and DCP correction have also been slightly modified. And in most cases, we get similar results. You basically get a QZ4P quality at the cost of a TZP basis set, and you get really good results for pi interactions and conformational energies, as you have seen. You could say that the versatile Swiss Army knife r2SCAN-3c is available too for everyday problems. So I can highly suggest to use it if you just need a a fast estimation for any energy. And it should be available in the next ARMS release, so in 2023. If you're interested, you could also read the papers. So I put the QR codes over here. Right, so now I'm switching back to my desktop to give you a short demo. So I have an input over here. So for example, if you want to calculate single point calculation for this phenol molecule over here, and you can just open it with the GUI. And for the exchange correlation functional, you can then choose the meta GGA, then r2SCAN-3c. And normally you would think, okay, you should also set the basis set and frozen core and so on, but you can simply run it or save it. So for example, like this, then you get a warning, okay, activated basis set MTZ2P and frozen core none needed by r2SCAN-3c, so the GUI sets it automatically. Also the numerical quality. Right, so now it should be running. While it's running, I want to show you the input. So basically it looks like this. So you can see that it sets the basis, so the MTZ2P basis set, the core is set to none, and the numerical quality is set to good. And the meta GGA keyword r2SCAN-3c is set here. And with that, the D4 correction and the DCP correction are also set automatically. So you don't have to do that in the input as well. So now the calculation is already converged, I guess. So we can look into the outputs. If we scroll down, we see, okay, it's finished, normal termination, that's good. And we can check if there's a D4 dispersion correction. You can see the parameters over here. And I also want to show you that the GCP correction is there, which you can see in this block over here. And both of them are already included in the total energy down here, so you don't have to do anything anymore. All right, before I finish, I still want to give some acknowledgements. So going back to my slides. So here on the right side, you can see our work group in Bonn. Of course, I want to thank my PhD supervisor, Stefan Grimme, for letting me work on this project. Then I want to thank Markus Bursch, who supervised this project. Also Julius Kleine-Bühning, or formerly Stückrath, who worked with me on it. Then I want to thank some people from SCM, especially Erik van Lente, who helped us if we had any questions, and also the final implementation in the GUI. And yeah, lastly, I want to thank Fedor and Matti for inviting me and letting me talk here. And of course, I want to thank all of you for your attention.
Thank you, Thomas. That was yeah, very nice and clear overview of all the different aspects that may lead you to use r2SCAN-3c as a Swiss Army knife, as you suggested. So yeah, let's take some questions from the audience. You can type in questions in the chat, and I'll see if I can allow people to unmute themselves. So I think that should be possible now. So I see somebody raised their hand. So yeah, Arno, you should be able to unmute yourself. Otherwise, you can type.
Yeah,
in the chat.
I think you can hear me, right?
Yeah.
Yeah.
Yeah, you cannot see me because I'm not available to share my video. But well, thank you, Thomas, for your nice talk. I have a question actually. So you showed in the beginning, you have by now quite a nice array of these 3C methods, like for different functionals. And especially when you consider double hybrids, you have typically in practice quite huge problems with basis set errors, because the MP2 contribution will converge very slowly to the basis set limit. So then I was wondering if you have considered also doing a 3C parametrization for double hybrid.
Actually, we don't, since we want to have very fast computations with these 3C methods. So we currently working on a rate separated hybrid, but I think we won't go further than this. I think we won't go to double hybrids anymore.
Okay, thank you.
Yeah, well, something you could do yourself, Arno.
I might. Thank you.
Good. Any other questions from the audience? Okay, so I have a question in the chat here, Thomas. I'll read it out.
Mm-hmm.
So do you have essentially a counterexample? When should you definitely not use r2SCAN-3c for the STO implementation, or in general?
I think there shouldn't be any problem where you definitely not should use it. Sometimes you need a fork exchange. So if you know that you need fork exchange, of course, then you have to use the hybrid. So but still, I think with r2SCAN-3c, you always get a good estimation.
Okay, yeah. So I guess as you showed for the transition states, typically there you would underestimate the barriers, and
yeah, right.
Yeah, rather go with a hybrid.
Yeah. Right. Here you can see this, for example.
Yeah. Okay, that's clear. Any other questions? Okay, so maybe if somebody still has a question, of course, they can type. So I have a question about the geometrical counterpoise correction. So you mentioned it's essentially for free. Could you explain a little bit more how it works in the 3C scheme as you implemented it?
So basically, we have a standalone program of the GCP correction, and we just call it within ADF. So it's a very fast calculation. You only need the geometry which goes in, and the rest is just fitted, and you get the correction out of it. So it's a bit complicated. So if you want to have it in more detail with every formula, maybe it's better if you read the paper.
Yeah, okay, good. But essentially, it defines the fragments automatically and then calculates the differences.
Yeah, it doesn't depend on the fragments itself. I think it's somehow it has something to do with an overlap integral that has to be then calculated, and then you only need, yeah, just one molecule basically.
Okay, good. Yeah, so if we want to use that for other applications, we can use the GCP standalone as well then.
Yeah, right.
Good. Another question from the chat. So is the 3-body correction term from the D4 corrections new in ADF?
No, it should not be new. So the default dispersion correction is always does always include the ATM term.
Okay, good. But yeah, I guess maybe it wasn't. So you specifically reskilled it for this this scheme?
Yeah, right. Yeah. I also changed these beta and gamma parameters. They are just charge dependent parameters. I added those to the code, but the rest was already available.
Right. So, but if one would use D4 in ADF, you would get the normal, the original scaling.
Yeah, right. Yeah.
Good. Okay, let's see if there's any other questions. Well, if not, if you do have any questions later on, feel free to send them to SCM, and if we can't figure it out, we'll forward it to Thomas. He'll be happy to answer them.
Yeah, of course.
Good. Okay, so thank you again, Thomas. Thank you everyone for listening in, and have a good afternoon.
Yeah, thank you for having me as well.
All right. Bye-bye.
Bye.
Thank you. Bye.